Okay, this is our list of the work that we have concluded so far using the position vector that is being manipulated or operated on by the del operator. And this, of course, is our definition of the position vector. It is just the coordinates of some point in three-dimensional space. The magnitude of it, that's a function of x, y, and z. It's the square root of x squared plus y squared plus z squared. We've shown that the divergence of position vector is 3. The curl of it is 0. And we have also shown that if you take the gradient of the magnitude of any position vector r, here be the magnitude of any position vector in general, if you take that gradient, you end up with the unit position vector. And we've also shown that if you take the gradient of the magnitude of any position vector raised to the nth power, it's equal to this equation. And in the previous videos, we've also demonstrated that this equation here is actually a manifestation of this more general expression here. And then we've also shown that if you're taking the divergence of the scalar vector, which is being multiplied by some function of r, it's equal to this expression here, 3 times the scalar function plus r times the derivative of the scalar function. And then we also demonstrated that the Laplacian of the magnitude of the position vector raised to any power n, that's equal to n times n plus 1 times r to the n minus 2 power. So for example, if we were taking the Laplacian of 1 over r, where n equals negative 1, then we have negative 1 plus 1, that's 0. So here, the reciprocal of the magnitude of the position vector, that's an example then of the harmonic function. And remember now, when we're talking about Laplacian, this is really shorthand notation for this, where we're taking the divergence of the gradient of the position vector, the magnitude of the position vector raised to the n power. But now, just like this equation here is a more specific manifestation of this general relationship, this equation here is actually a manifestation of this more general vector identity. We're taking the Laplacian of any type of scalar function of r, not necessarily just r raised to the n power. You get this identity. And we haven't proven this yet. So that's what we're going to do in the next video, is prove this identity, and then that will conclude our section of the position vector and the different identities that result when the position vector or its magnitude is being operated on by the del operator. So come back, join us for the next video. We will prove this expression. Then when we have that finished, we'll get on to other topics in vector analysis.